Okay, so I learned how to make videos, and I am in the building, but I am downstairs. I'm grading Academy entrance exams today. And so yesterday in the B-Day classes, they took these notes by hand, just like you are going to. But they got the live show. So you've got the recorded version. So basically on your own paper, you want to take down these notes. At any point the video is going too fast for you, just pause it and write down what you need, and then you can resume it and pick up where you left off. So today we're going to be talking about graphing exponential and logarithmic functions. So I want to start that discussion by revisiting the basic functions that we talked about in Magnet Advanced Algebra. So the basic exponential function would be y equals 2 to the x power. So the base is 2 for our parent function. The reason why we use 2 is because it wouldn't make any sense to use 1, because 1 to any power is still just 1. So then the next logical choice was to use 2. And so since exponential functions and log functions are inverses of each other, if we want them to truly be inverses, then the log should have the same base as the exponent. So our parent log function, we're going to say, is y equals a log base 2 of x. So what's true about inverses is that you're switching x and y. So everything that's true about the x or the domain in 1, for its inverse, it would be true about y. So let's write down that basic information. Let's start with the asymptote and the domain and range. For your exponential function, we have a horizontal asymptote, which will normally be the x-axis if there's no transformations taking place. So if it's horizontal on a cx-axis, the equation would be y equals 0. The domain of all exponential functions is negative infinity to infinity. And the range would be 0 to infinity. Based on where the asymptote is, you would use a parentheses on that 0 because of the asymptote. So if the asymptote for the exponential function is horizontal and the x-axis, then for its inverse, it would be vertical and be the y-axis and have an equation of x equals 0. If the domain of the exponential function is negative infinity to infinity, that would become the range for its inverse. And if the range is 0 to infinity, that would become the domain of its inverse. Okay, so you can graph anything with a table of values. I hope you know that. So normally you're in charge of the x's. Well, we've got these patterns that are evident with exponential and log functions. So we specifically are going to choose 0, 1, and -1 as our x values. And if you plug these x values into your exponential function, you know that anything to the 0 power is 1, 2 to the first power would be 2, and 2 to the -1 power would be 1 over 2. Now, what you want to notice is that this is specifically the base of the exponent, and so this would be 1 over the base. That's going to be important because we're going to switch to a base of e when we start talking about the natural log and graphing y equals e to the x. So we want to just make sure that we understand that this is always going to be the base of the exponent, and this will always be 1 over the base of the exponent. Okay, so if I change this to y equals 3 to the x, this would be a 3, this would be a 1/3. Y equals 5 to the x, the order pair would be 1, 5, and -1, 1/5. So we can graph those points. If I remember, I usually like to graph my asymptote first. It kind of just gives me a heads up of what I should expect with my graph. So there's my asymptote. With an exponential function, your point should be all above the asymptote or all below. So if you draw your asymptote in and then you start to get points going above and below, you know something's off. So, and I have a y-intercept. That's kind of a base point for exponential functions, the 0.1, 2, and -1, 1/2. So over here on the left, you want to hug your asymptote and then curve up through the points. Okay, so that's your general shape of an exponential function with the horizontal asymptote and then curving up. It's growing very rapidly. It's kind of a common expression to say something grows exponentially. An example would be the growth of Starbucks. Started with 1 Starbucks, and in a few short years, they had Starbucks all over the country. That would be an example of exponential growth of a business. So since we talked about earlier how exponential functions and logarithmic functions are inverses of each other, and inverses mean that everything about x and y switches, we used our x's were 0, 1, -1 over here. So that should be our y's for a log function. And then all the values we had for y should switch over to x. Again, I want to make the point that this value of 2 is the base of the log, and 1 over 2 is 1 over the base, so that we can just refer back to that for that pattern when we change the base to e. So this time we have a vertical exponent. We have, instead of a y-intercept, we have an x-intercept, then the point 2, 1, and 1/2 -1. Again, hug the asymptote, but then curve up through those points. Okay, so you can see the similarity of the curves here. Now, this is not always the way these are going to look. They're going to have the same general shape, but we can move these graphs around with transformations so they can have the same curve but in different directions. If I take this exponential curve and it got reflected over the y-axis, then this is the way the graph would look. Or if I took the blue graph and I reflected it over the x-axis, then it would look like that. Or if I reflected it over both the x and the y, then it would look like that. So the curve is going to have the same general shape, but it doesn't necessarily go in the same direction every time. Same thing for natural logs. If it gets reflected over the y-axis, it would curve up like that. If it got reflected over the x-axis, it would curve down like that. And if it got reflected over both the x and the y-axis, then it would curve like that. Okay, so general shape is same, but you shouldn't always expect it to look exactly the same in the exact same direction. Okay, so let's move on to what if the base is e, and what if we put some numbers in here and there's some transformations. Okay, so here are the graphing forms for exponential and log functions. I've already made the base e, so if you were referring to what we just talked about, that could be the 2. That was the base of the exponent before, and this could be log base 2, but we are specifically going to concentrate on graphing with the base of e, so that's why I put the e in the natural log there. Notice we have 4 variables for transformation, a, b, c, and d. So you guys should be used to AH and K. Most of the stuff that we graphed, we had an AH and K. Back at the beginning of magnitude algebra, when you learned about basic functions, we had like 8 transformations, and we had an A and a B, and then an H and a K, and then some other ones. So when you graph trig functions, though, we have A, B, C, and D. So it's like if there's 4 transformations, whoever decided way back when wanted them to be in alphabetical order. So the good news is C and D are really the same as H and K, and you should really know what to do with those anyway. All right, so we're going to just take some notes on these 4 different kinds of transformations. The first is the A value. Just like it is for any other function, the A value represents a vertical stretch or shrink. That should be or vertical stretch or shrink. So what would really happen is it multiplies the y values by the A. If it's negative, it would reflect the graph over the x-axis. Okay, so if you were trying to be mathematical, you would describe an A transformation as a vertical stretch or shrink. How you would literally affect your values on your graph, you would multiply all your y values by whatever your A value was. So it just affects the y values. And if it's negative, if the A value is negative, the result would be a reflection over the x-axis, which would have the result of making all your y's the opposite as what they started out as. Okay, and that would be for the same for both functions. Right, so then we have the B transformation. You did learn about that with transformations in magnitude advanced algebra. That is a horizontal stretch or shrink. Apparently, I keep making the same mistake. It multiplies the x value by the reciprocal of B. So The things that affect y are pretty much at face value. They do what you would think they would do. The things that affect x often kind of do backwards of what you would think. Like when we move left or right, we do opposite of the sign. So if it affects x, we're not multiplying the x values by the b value, it's by the reciprocal of the b value. So if this one is negative, then it's going to reflect over the y-axis, which would have the net effect of changing all your x values to opposites. Next is C. So C and D are pretty easy. You just have to remember what H does. Okay, C is just like H. It shifts things right or left, and it will go opposite of the sign. And then you have the D value. The D value is just like K. It shifts things up or down, and it goes with the sign. The C and the D are also going to relate to our asymptotes. If we move things up or down, that would affect a horizontal asymptote. If we move things right or left, that would affect a vertical asymptote. So the C and the D are going to have some effect on changing our asymptote and corresponding to whichever the domain or the range, depending on if it's vertical or horizontal. One thing, when you get a handout, you want to make sure right here that you add in these parentheses, because something that would be important is if the function has both a b and a c value, they have to be factored apart. So you would want to make sure you add in these parentheses when you get your handout, because the parentheses are missing. You need the b separate from x minus c. And here, the same thing. So you want to add in an extra set of parentheses there. If you don't do that, you're going to use the wrong c value in your graph. So that's sort of important. And sometimes it'll be given to you where they're already factored apart, and sometimes not. So you have to remember that. Okay, so like I said, if you're having trouble keeping up, then just pause the video. We're going to move on to actually graphing y equals e to the x and y equals the natural log of x. So we're going to use the information that we went over with the parent functions where the base was 2, and we're just going to transfer that same information to what if the base is e. So it's really not much in the way of new information. It's just sort of taking what we already talked about and making the change to a base of e. Okay, so let me change my color. All right, so if we do y equals e to the x, okay, so same as 2 to the x, except now the base is e. So if we do our table, we're going to use those same x's, 0, 1, and -1. And it doesn't matter what the base is, anything to the 0 power is 1, e to the first is e, and so e to the -1 would be 1 over e. So where I wrote the base and the 1 over base, notice that's the base. You probably want to commit these values to memory. E is about 2.718. You all know that pi is 3.14, so you should know that e is 2.718. And 1 over e, you're going to have to graph that, so you want to know that that's 0.368. Not a big deal if you don't know that specifically, but you need to know it kind of so that you can plot it on a graph in a semi-accurate way. Okay, so if we graph those points, so just like the other, the function with the base of 2, it still is going to have an asymptote of the x-axis because we haven't made any transformations. And we have the point 0, 1, 1 comma e. So 1 comma 2.78 and -1 comma 1 over e, and so -1 and then 0.368. So if you compare the two graphs, they look very similar. They should look very similar, just a little easier to plot the points when 2 was the base. The domain is still -infinity to infinity. The range is still 0 to infinity, and the asymptote is still y equals 0. But if we think about some of these transformations, the way that you can get an asymptote to move is if they're shifting up or down. Moving right or left doesn't affect a horizontal line, but up and down definitely. So if there is some shifting up and down, which is the d value, then your asymptote would just be y equals whatever the d value is. The range would either be d to infinity, or if it curved below the asymptote, it would be negative infinity to d. So let's do the same thing with the natural log function, which is just log function to base e. All right, so just like before, if the x values for the exponential function were 0, 1, -1, we want to make those our y values. And the y values, we want to make the x values. So then we can plot that. All right, so now we have the vertical asymptote. There's been no shifting right or left yet, so vertical asymptote is still the y-axis. Got the x-intercept as opposed to the y-intercept over here. E 2.718, comma 1, and 1 over e is 0.368, -1. So again, this should look a lot like what you graphed when the base was 2, except the points were a little harder to plot. So the range is still negative infinity to infinity. The domain is still 0 to infinity, and the asymptote is still x equals 0. But if this graph shifted right or left at all, that would affect where the asymptote was. So if that happened, the asymptote should be x equals whatever the c value is, which would make the domain either c to infinity or negative infinity to c, depending on which side of the asymptote the points were. All right, so the last thing we're going to do is we are going to do a couple of examples, one of each, so we can kind of just walk through how we take this information and what do we do if we have some transformations. Okay, so for our exponential function, we're going to use y equals e to the x minus 3 power plus 1. So set your table up. Same values that we've been using, x values 0, 1, -1. The y values 1, the base of e, and then -1, 1 over the base of e. Okay, but for this function, we have some transformations. This is the c, which is the same thing as h, and this is the d, which is just like k. So this transformation tells us to move right 3 and go up 1. Okay, so right off the bat, I know, again, if it's exponential, it has a horizontal asymptote, and moving the graph up or down is going to affect that. So I know that my asymptote is going to be affected. As far as the points in my table, I can use those basic points and then just put in the transformations over here. If I go right 3, that would be the same as adding 3 to all the x values. And if I go up 1, that's the same as adding 1 to all the y values. So now I can plot those points. All right, so I know, again, because I'm moving up 1, then it's going to also shift my asymptote up 1, up off the x-axis. And then this point would become 3, 2. This would be 4, and then e plus 1. Remember, e is 2.718, so this would be 3.718. So 4, comma, 3.718. And then this would be positive 2. 1 over e is 0.368, so plus 1 would be 1.368. So 2 and 1.368. And you can draw in your curve. So notice the domain is still negative infinity to infinity. That's going to be the case for all exponentials. The range is 1 to infinity, and the asymptote would be y equals 1. Okay, so one more example. Let's do one with the natural log. And we'll make this one a little bit more interesting. We'll put in a reflection. Okay, so y equals the opposite of the natural log times quantity x plus 2 minus 1. So let's start with the easier transformations. This would tell you to move left 2, and this would tell you to go down 1. In terms of the asymptote, moving left or right would move a vertical asymptote, so I know that my asymptote is going to move 2 to the left. Okay, this is the a value. If the a value is negative, it reflects over the x-axis, which has an effect of making my y's the opposite value. Okay, so let's think about that for a second. If you reflect something over the x-axis, okay, so specifically, I'm going to go back to my log graph here. If you reflect this over the x-axis, then the part that's below the x-axis will flip up above, and the part that's above will flip down below. So the negative y's will now be positive, and the positive y's will now be negative. So when I set up my table, that's what I want to think about, is that this negative is going to make all of my y values opposite. Okay, so I'm going to start out with the same table. So the x's for exponential were 0, 1, negative 1. Remember, that's the y's for log. And the y's were 1, e, and 1 over e. So that's going to be what I write for the x's. And you feel free to write the decimals there instead. You don't have to write the e and the 1 over e if you're doing that. Okay, here's the deal though. With transformations, when you move left, right, up, or down, that should be the last thing you do, kind of like order of operations. So if there's any reflecting or multiplying, you want to do those things first, then worry about moving left or right or up or down. So the first thing I'm going to take care of is this reflecting over the x-axis, which is going to make my y's opposite. So I'm going to make all the y's opposite. There's no such thing as opposite 0. But 1 will turn into negative 1, and negative 1 will turn into positive 1. Okay, so that's what happens when you do the opposite y's. Then I can worry about the fact that I'm moving left 2 and down 1. Left 2 would be subtract 2 from your x's. And down 1 would be subtracting 1 from the values that I just got when I thought about the reflecting. Okay, e minus 2, that's pretty easy because e is 2.718, so you subtract 2, you just have 0.718. 1 over e minus 2, 0.368, you might have to think about that a little bit more. It's actually negative 1.632. You could estimate that as long as you're pretty close. So let's get that graphed. Okay, so we know that if we move anything left or right, that's going to move a vertical asymptote. So my asymptote should be over here because I moved everything left 2. So if you move left from off of the y-axis, that's where you are. The first point, 1 minus 2 is negative 1, and then 0 minus 1 is negative 1. So I have negative 1, negative 1. E minus 2, so 2.718 minus 2 is 0.718, and negative 1 minus 1 is negative 2. So 0.718, negative 2. And then lastly, the 1 over e minus 2 comes out to be about negative 1.6, and 1 minus 1 is 0. And my curve goes like this. So the domain is the negative 2 to infinity. The range is always negative infinity to infinity, and my asymptote is x equals negative 2. Okay, so that's all the notes that I gave to my B-Day classes. So if you have these, you're at the same place they are. The next thing that I want you to work on is a handout, which looks like this. Make sure you add in that extra set of parentheses on both sides. Make sure you use your notes to accurately get your apparent graph, because if you don't have the right starter graph, then that pretty much spells disaster for the rest of it. And make sure, again, you add this extra set of parentheses right here. Okay, so after you get the notes, you guys can work together to work on this handout. And then after that, you can get your quiz review. The graphing is on the quiz review, but as of right now, it's not on the quiz. I'm thinking about adding a bonus or something, but I'm not quite there yet. So work on this, and then when you get this finished, then you can get the quiz review. It's a half sheet. That's what I'll be checking for homework on Monday, and we will go over before your quiz on all of the log and exponential stuff minus the graphing on Monday. Okay, hope this went well. Hope you learned something.